Hello and welcome back. Today we're going to go over the ideal gas law and also Dalton's law. So this is going to wrap up our videos on gases. Keep in mind we've already gone over Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. So now we're on to just the last little bit. You're looking at the ideal gas law. The ideal gas law is pressure times volume equals moles, that's what this N stands for, times a gas law constant times temperature. This gas law sort of throws people for a loop because there's this whole idea of a constant in here. What is this constant? Well, the constant is a number that you know based on the units that will never change. Think of a number like pi or the speed of light or something like that. It's a number that's not going to change that you insert into this equation to be able to rearrange it. This constant is based on the units here. So for instance, the R will equal 0.0821 if you're using liters times atmospheres times moles times Kelvin. However, this constant will equal 8.31 if you're using kilopascals instead of atmospheres. And then notice it's going to be even different if you're using millimeters of mercury. So the moles, the temperature, and the volume are always the same units. But the pressure can change. So you have to use the correct numbers. Also, in these problems, if they give you a volume in milliliters, obviously you're going to have to convert to liters, otherwise it will be wrong. If they give you a temperature in Celsius, you got to convert to Kelvin. So this is where people miss these questions. They just sort of do them fast and they don't pay attention, and then they don't convert one of these units and they will get it wrong. Let's go ahead and do a few practice problems. I always write out my equation first. Pressure times volume equals nRT. How do I know when to use the ideal gas laws versus some other gas law? Well, first of all, if they ever ask you for moles or quantities in a gas law problem, then you will most likely have to use this ideal gas law. Because remember, there's no moles in any of the other gas laws. If I have 4 moles, so that's going to be 4, of a gas at a pressure of 5.6 atmospheres, the pressure is 5.6. Let me get a little bit more room here. Pressure is 5.6 and a volume of 12 liters equals 4. Okay, so we have 4 moles here, 5.6 atmospheres, and 12 liters. What is the temperature? Well, I have to first of all insert my constant. I don't know what the temperature is. I'm looking for that. What constant do I use? Well, if I have moles, atmospheres, liters, moles, atmospheres, liters, I'm going to use 0.0821. This is the most common one, really. 0.0821. Now I have to rearrange the equation. I need to get the T isolated on one side. So basically, if I multiply both sides by 1 over 4 times 0.0821, I would have to do it on this side too. 1 over 4 times 0.0821. This side's going to cancel, so I'm going to be left with T on this side. And on this side, I have this big jumble of numbers. So, T equals 5.6 times 12 divided by 4 times 0.0821. And if I do that math, I will get somewhere around 204.6 Kelvin. Okay. Moving down, pressure times volume equals nRT. I want to put all the units in here so you understand how these units work. If I have an unknown quantity of gas, that means moles. I don't know the moles. At a pressure of 1.2 atmospheres, pressure 1.2 atmospheres, and a volume of 31 liters. 31.0 liters. Let's just put 31 liters. I don't know the moles. A temperature of 87. I need to convert the 87 to Kelvin. Never forget that. 273, 360 Kelvin. Now I need to use my gas law constant, which is 0.0821. And there's actually units here. Liters times atmospheres over Kelvin times actually I need to go back because I'm having a brain blank right here. Oh, sorry, moles times Kelvin. Sometimes that just happens when you're doing chemistry. So that's why all these units cancel out, really, when you think about it. If I look at these units here, and when I rearrange it, they will actually cancel out and just leave me with the final unit I need for the answer. In this case, it'll be moles, because I don't have moles in here. For instance, the Kelvin will cancel, right? So, how do I get the moles on one side? N is going to equal 1.2 times all this divided by this stuff here. So it's going to be divided by 360 Kelvin times 0.0821 liters times atmospheres times Kelvin times moles. If I do that math, I will get somewhere around 1.25 moles. Now, yet again, though, look at this. The liters are going to cancel. This is on top. The atmospheres are going to cancel. The Kelvin cancels. And in the end, I'm just left with moles. Okay. If I contain 3 moles of gas, so I got pressure times volume equals nRT. 3 moles of gas in a container with a volume of 60 liters and at a temperature of 400 Kelvin. So temperature is 400 Kelvin. What is the pressure? I don't know this pressure. Yet again, I'm going to use 0.0821. I'm not putting all the units in right now. So how do I get the answer for this? I just need to divide this side by 60. That's going to go over there. Essentially what I'm doing is multiplying both sides by 1 over 60. This side by 1 over 60, this side by 1 over 60 to isolate the P on this side. If I do that math, I'm going to get around 1.642. You know, honestly, I feel like a lot of chemistry teachers just assume kids know this math, and they don't. And that's not a bad thing at all. If you don't understand the math, there's no shame in raising your hand saying, hey, you know what? How did you get that? How do you isolate this? Can you refresh me on this basic math here? Because just because it's entry-level math doesn't mean it's easy, and it doesn't mean people remember it. Trust me. So we should never assume people know anything. And I don't mean that in a bad way. All right, moving down. If I have 7.7 moles, pressure times volume equals nRT. See how fun it is just to say that? 7.7 moles, 7.7 moles at a pressure of 0.09. So my pressure is 0.09. And at a temperature of 56. Yet again, convert the 56 to what? Kelvin. So this is going to be 329. So I got 7.7 times 329 times, now I need my gas law constant, 0.0821. What is the volume? I have my pressure. I don't have my volume. So I have 0.09 times my volume equals all of this jumbled mess. Yet again, essentially, I'm going to multiply both sides by 1 over 0.09, but in the end, that's just going to move this 0.09 over here. So now I'm going to do that math. 7.7 times 329 times 0.0821 divided by 0.09. And if I do that, I'm going to get somewhere around 2,310 liters. Okay, moving on. That was all for the ideal gas law. Let's go to something called Dalton's law. Dalton's law says that if I add two gases together, then my total pressure will equal the partial pressures of both gases. So whatever the pressure was in here, plus the pressure in here, will equal the pressure in here. If you see that, they sort of added up these pressures over here. And notice how all the little particles are together now. We've combined the gases, and our total pressure will equal the pressure of the two gases in here. Well, that seems moderately basic. Let's see what we can do with this. A container contains three gases. Let's just draw this little container. It has N2, so it has nitrogen. It has O2, oxygen, and argon. With partial pressures of 23.3, so that's 23.3 kilopascals, 40.9 kilopascals, and 13.7 kilopascals. What is the total pressure? Well, my total pressure will equal all of these combined. The entire pressure in here will equal all of these. So I just have to add these up. 23.3 plus 40.9 plus 13.7. And if I do that, I'm going to get around 77.9 kilopascals. You're thinking, wow, that seems easy. No problem. Well, it gets harder. I always say chemistry is easy until it's not. Down here we have in the chem lab, a student filled a balloon. We've got a balloon with two different gases, CO2 and N2. The atmospheric pressure in the chem lab was 770.0 millimeters of mercury. This is a little bit different. You're thinking, wait a minute, what does that have to do with the balloon? If we think about it, this is not some sort of rigid container like some aerosol can. So the overall total pressure of this balloon is this pressure that's being exerted on it. So our total pressure is 770.0 millimeters of mercury. The partial pressure of CO2 is 0.3255 atmospheres. What is the N2? Well, they're throwing us for a loop now. I have 0.3255 atmospheres, but this is in millimeters of mercury. So really I just need to convert it. 0.3255 atmospheres. What is that in millimeters of mercury? Well, 1 atmosphere equals 760 millimeters of mercury. Notice how we can now cancel out our units. I will multiply this, and I'm going to get around 247.38 millimeters of mercury plus N2. So now I just take 770 minus 247.38, and it's going to equal my N2. And that's going to be around 522.62. Okay? All right. Let's go ahead and move on down to the next one. In a lab experiment, now these next couple are kind of difficult. I threw these in just to kind of show you that you are capable of more than you think. In a lab experiment, which was done with a barometric pressure of 1.0433 atmospheres, some H2 was collected over water. This is difficult. First of all, you have to understand vapor pressure. We have a container. Now, the overall pressure is, the total pressure is 1.043 atmospheres. It's around here. There's some water in here. It's liquid, obviously. And you're thinking, well, that's not a gas, so what does that have to do with what we need? Well, in this container, there's some hydrogen. You're thinking, well, okay, there's just some hydrogen here and there's some liquid water here. Why are they even telling me this? Well, remember that in a closed container, some of this water has enough kinetic energy to break free of its intermolecular bonds, and now it's actually basically gas. This is vapor pressure. So essentially we have hydrogen and H2O gas in here. So our total is going to be 1.043 atmospheres plus equals H2, the pressure of H2 plus whatever this pressure of hydrogen, of H2O is. So how do we find any of this? We need to know one of these to get the answer. Well, this is where you actually have to know that if you go to the internet and look up vapor pressure of water at 27 degrees, it's going to give you the number. It's 26.7 torr. So really, they should have given you that number here on the test. But yet again, we have a problem. This is in atmospheres. This is in torr. So I need to convert. Well, 26.7 torr. I know that 760 torr equals 1 atmosphere. So I'm going to take 26.7 divided by 760, and I'm going to get 0.035. Now all I have to do is 1.043 minus 0.035 equals H2. And it's around 1.008 atmospheres. So they're trying to throw you for a loop with that vapor pressure question. All right, down here. This is definitely the hardest question here. 75 milliliters of a gas was collected over water at 22 degrees. So yet again, we have a container. We have water. We have a mysterious gas in here. We don't even know what it is. We know that we have a volume here. The volume of this gas is 75.0 milliliters. Yet again, I got to take 22 degrees Celsius and look up the vapor pressure of water at 22 degrees Celsius. And if I look that up, I'm going to find 19.8 torr. Okay? All right, but I'm going to need to convert this 19.8 torr into something useful. Well, I noticed the total pressure is 749.8 torr. So I have the pressure of this water vapor, and I have the total pressure. Now I can find the pressure of this gas. This is where I use Dalton's law. 749.8 equals 19.8 plus whatever my mysterious gas is. So my mysterious gas is 749.8 minus 19.8. That's going to be my pressure, which is about 730 torrs. So I have a volume. Now I have the pressure on this mysterious gas. They already gave me a temperature here, which was 22 degrees. But I need to convert that. 22 plus 273, right? So it's 295 Kelvin. Okay, this is where things get a little crazy. It says, what will the volume of this gas be at standard temperature and pressure? Okay, so now we're going to change up the temperature and pressure. We don't know what the volume is. We want this new volume. What is standard pressure? Well, it's 1 atmosphere. 1 atmosphere is 760 torr. What is standard temperature? It's 0 Celsius. 0 Celsius is 273 Kelvin. All my units match here. So what law do I know? What gas law do I know where if I have pressure, temperature, and volume, and I have a new pressure, temperature, and volume, I can figure this out? And the answer is, I'm just going to write it up here, the combined gas law. Pressure times volume over temperature equals pressure times volume over temperature. So now I have to put in all the numbers, plug in 730 torr in the pressure, plug in my volume, plug in my temperature, rearrange the equation, and do the math to get this new volume. And if I do all of that, I'm going to get around 66.6. Yes, it's a strange number to get out of this because it's a difficult question. Milliliters. That is a difficult problem. You have to know water vapor, Dalton's law, combined gas law. But I just wanted to show you that to make sure that you should be aware that you can start combining these equations and using them all in one problem. We have to build on our knowledge that we're learning from chemistry. And that can be difficult. It's kind of like math, it builds on itself. Okay, really fast. These are 3 questions from a standardized test in Virginia on chemistry. And I wanted to show you the types of questions you would be likely to get on Dalton's law. A mixture of gases with a pressure of 800, so our total pressure is 800 millimeters of mercury, equals 10% oxygen, so here's O2, that's 10%, plus 90% nitrogen. What is the partial pressure of the oxygen? It just gave us a percentage, but what's the actual pressure? Well, when I think about it, it's 10% of whatever this is, right? It's 10% of 800. How do I get 10% of 800? Well, a lot of kids just sit there and guess. Not guess, but they kind of figure it out in their heads. But if you think about it, how do I get this number to begin with? I have some number. I divide it by a total, right? I multiply by 100, and then I get 10%. So what happens if I reverse this entire process? Okay, I don't know what this number is. I have 800, I have times 100, I have 10%. Well, first of all, I could just put this 100 on this side. I can multiply both sides by 1 over 100. And so if I do that, I'm going to get 10% divided by 100. And if I take 10 divided by 100, I'm going to get 0.1. Essentially what I'm going to do is turn that percentage back into a decimal. Okay? Now I just have to say, well, x equals 800 times 0.1. And if I do that math, I'm going to get 80 millimeters of mercury. Okay? Now, the other way I could do is to say, well, wait a minute, what's 10% of 800? I know 10% of 100 is 10. So 10 times 8 is 80. I could do it that way, but I wanted to show you this way because then I can figure out no matter what numbers I'm given, even if those are difficult numbers. Okay, moving on down. In a mixture of oxygen and nitrogen gas, 80% of the total gas pressure is exerted by the nitrogen. So we have nitrogen, oxygen, and we have a total. 80% is nitrogen. That means 20% has to be oxygen. If the total pressure is 2 atmospheres, what pressure does the oxygen exert? Yet again, I just do the same thing. My equation is going to be, I'll just put it up here, 2 atmospheres. %. So essentially, yet again, divide the 20 by 100. Okay? And if I do that, I'm going to get 0.2. So essentially, it's 0.2 times 2.0, and I will get 0.4 atmospheres. Going on down, last one. The composition of dry air is 78% nitrogen, 21% oxygen, and 1% something else. What is the partial pressure of nitrogen at standard atmospheric pressure? Well, okay, so it's 101.3 equals, and then we're going to do exactly the same routine, and in the end I'm going to get 79. Now let's just think about this logically for a second. They're giving me the answers here. I know that nothing can be greater than 101.3. In fact, there's no way it can even be 101.3, so it can't even be this one, and it can't be that one. So, and nitrogen's 78%, so it feels like it's got to be higher than 21, so you can just kind of guess on this one. You know, same thing with these other ones. That's the beauty of standardized tests, or it's the negative thing about them. You can just guess the answer sometimes. Okay, well, I know that's a long video. I hope that helped you out. We're done with gas laws, but yet again, if you have any questions, let me know. And